Welcome back to CTN. I'm Robert Van Sluten. This is the first of 4 episodes on recursion. Let's get started. What I want you to think about is, does this program run infinitely? It's technically recursion. The function is calling itself. It may seem to, but the answer is no, because what ends up happening every time a function is invoked, things are pushed onto the stack. Its parameters and also its return address, where to go back to. Now, if you do this continuously, what's going to happen is the stack is eventually going to overflow and the program is going to crash. So every recursion routine needs some form of stopping condition. In this case, you do an if check to determine whether you're at 10 yet. If you're at 10, you return. So it's going to iterate. It's going to start at 0 and go to 9. Now, does this really have any value? Because it's no different than, let's say, a simple for loop. So we're not there yet. What the general routines usually have in them is you have the stopping condition, but you also have some kind of iteration, for loop iteration of some type, that surrounds the recursion. And the data gets modified, the calling data gets modified in some sense that you want to process multiple times. So effectively, you're forming a tree. You're branching out. You're doing the same thing multiple times in a different way, different pieces of data. Now, if that doesn't make sense to you, it's going to become clearer when we start looking at an example. If I have the sequence A, B, C, D, how many combinations can I put those in an order? In other words, if I've, the first one's A, B, C, D, I could have A followed by C, followed by B, followed by D, or I could have B followed by A, followed by D, followed from C. It turns out, this is the output of the code that we're going to review, there's 24 different permutations of that sequence. And you'll see how it varies here. It's a little hard to read because I know the characters are quite small. Let's analyze the problem. All right, if I have 2 arrays, one that I'm building, I'm trying to find a permutation, and the original set, instead of ABCD, I reduced it to ABC for simplicity. If I invoke the recursive routine for the first time, and I choose A at the head of the list, I now have a list with A followed by BC. If I pick B, I got AB with C remaining. If C is picked, this list is empty. That's the ending condition, termination condition. If I pop back up, I already did C. So I go up here, in that path I pick B. This time I want to pick C. So I have to know that I've already chosen B. So I have AC, B remaining. I go down, move it to the list. That's the terminating condition. Pop back up. Already know I've done this. I come back up. I've done A, I want to pick B. So I go down BC, and it continues this the same manner as you see in terms of the same pattern over on the left-hand side here. What's happening is each one of these levels is a recursion depth, okay, down to termination. Going across, 3 in this particular case, is the iteration of the loop. Now, one of the tricks is, after you've done A and you come back up again, you got to know to do B and not A. And you can do that with an index, or you could actually just swap A back to the end of the list. And as long as you know you only do 3 total, then that being trailing is okay. You actually need that, though, because when you invoke, when you go down and choose A, you want B and C to be on the remaining list. When you come down this way, you want A and C to be on the remaining list. Let's take a look at some code. What I have on the screen is an Xcode Playground. Now, after the next episode, which is about graphical recursion, I'm going to cover the pros and cons of playgrounds. And then we'll continue on to do some more recursion. I'm going to run this. You see down in the debug pane, it's the printout that I was showing you earlier. All the permutations for A, B, C, D, and there's 24 of them. All right, let's look through the code. I have a starting array, which is A, B, C, D, and I'm keeping a counter of the number of permutations that I find, and then I have the recursive function called perm. Now we go down the bottom. That's where the whole thing starts. I'm going to print the original array. I'm going to start the recursion. I'm going to give it an empty list and the remaining list, which is the full array. And then I'm going to print the number of permutations. Now, if we look at the recursive function, there's two parameters, there's two lists. It starts out with the empty one, starts out with the one that are so-called remaining. Now, my stopping condition is really if remain is empty. If it's equal to false, I want to recurse. So if it's equal to true, I go down to the else statement, and I up the counter, and I print the list. I print the list that I built. Otherwise, I'm going through the recursion. And I need a count. I want to know how many are in the remaining. Okay? And I also want an index into the list. Where's the next position? All right. I actually copy the two parameters into my own local parameters. And the reason for that is that when information is passed in via parameters, you can't mutate them. You used to be able to say variable in front of the definition means you can modify them. However, they took that away. I have a for loop. It's a for loop for my iteration. What am I doing? I'm going from 1 to count. I'm actually going through the number of items that are in the remain list. I pull, I do a remove, I do some array operations here. I'm removing from the remain, taking the next one. I'm assuming the next one I'm going to put in, and I append it to the list I'm building. Then I re-invoke perm. This is the recursion. The list I just made and the remaining list. Now, I'm going to iterate again eventually when I come back from the recursion. A bunch of returns will happen. I want to take the one that I just put on off the list because I want to use another one. What I do then is I just stick that one back on the remain list. So that's it. That's the entire operation to do this. It's not a lot of code. Let's go look at some mathematics. In mathematics, the number of permutations that results from a set of items is referred to as a factorial. The symbol is the number followed by an exclamation mark. As we've already seen, the factorial of 4 is 24. Now if I up that to 8, factorial explodes considerably to 40,320. It's very considerable given that 8 squared is only 64. If I have 52 playing cards, the possible combination jumps to 8 times 10 to the 67th, which is actually huge relative to a human. It's fundamentally infinite. The calculator you see on the screen is an application which implements a HP11C, just if you're curious, which happens to be my favorite scientific calculator. Let's go to the photo. It's going to be an interesting road ahead. Thanks for watching.